Hello friends, this is Animesh and welcome to the Get Mantra. So in this video we are going to do the question related to the mux, demultiplexer, decoder, encoder, what we have learned in our previous classes. So our first question is, this one is our first question. Okay, this one is our first question. So in first question it's written, consider the multiplexer based logic circuit shown in the figure. Okay, in this it's given 2 to 1 multiplexer and this 2 to 1 multiplexer. So which one of the following Boolean function is realized by the circuit? So it's asking the Boolean function which we are going to get at this output. Okay, at this output, right? So for 2 to 1 mux. Okay, for 2 is to 1 mux. Okay, there is a 2 input. Okay, I0 and I1, and there is one selective line, this is S. Okay, and here is the one output Y. So we know the how we are going to find the Boolean function of the output Y. This is S bar I0. Okay, plus S I1. Okay, this is the Boolean function for the output Y for the 2 is to 1 multiplexer, for the 2 is to 1 multiplexer, right? This we have studied in our previous classes. So from here we can say, okay, so from here we can say, what will be the output of this first 2 is to 1 mux. We are saying this P. Okay, we are saying this P, right? So P will be equal to, let me write red. Okay, P will be equal to, right, 1 bar, 1 bar. Okay, S1 bar W plus, okay, S1 W bar, right? So P will be S1 bar W. Okay, S1 bar W plus S1, okay, W bar. Here we will get W bar, here we will get. Okay, now we are going to get the output of this multiplexer. So here F, let's it's P. Okay, this is the P equal to, okay, so here the F will be equal to what, S2 bar, S2 bar, and P plus, okay, S2, S2, and this is P bar. If this is P, then this will be the P bar, then S2 and P bar. So here the S2 bar P plus S2 and the P bar, right? So see here one last option is given. Okay, what is this last option? W bar XOR P XOR, sorry, this last, let me shift here, this last option is given. Okay, W XOR X1 XOR S2. Okay, okay, then what we can say this, okay, F equal to X2. Okay, X2 XOR E, we can say, right, we can say this na, A XOR B. What will be the A XOR B? XOR B will be equal to A bar B plus A B bar, right? Like this, P X2 bar plus X2 P bar. Okay, this is the X2 XOR P, right? This is the X2 XOR P. And here what is this, what this is the, okay, this is same as this. Okay, A bar B plus A B bar, so W S1 bar and plus W bar S1. So this will be the P will be equal to the S1 XOR, okay, S1 XOR W. Okay, P will be the S1 XOR W, and F will be the X2 XOR P. That's why F will be equal to, okay, P, P XOR, okay, this one will be equal to the P XOR X2, sorry, this P will be equal, we have to put P here. What is the P? So P is the This is the PS1 XOR W, right? So F will be the X1 XOR W XOR, okay, S2. So here our option is F. Our boolean function for the output F will be equal to the W, okay, XOR S1 XOR X2, right? So see the option, our correct option is D, right? D is our correct option. So first we are in this question it's given 2 to 1 multiplexer. So we have got here P, okay, P, let P the output of the first 2 to 1 multiplex, and then P will be equal to the S1 bar W, S1 bar W plus S1 W bar, and this will be equal to the S1 XOR W. And the output of the second mux, that is second 2 to 1 mux, is S2 bar P plus S2 P bar. So this is the X2 XOR P, right? So if we are going to put the value of this P, okay, if we are going to put the value of this P, so F will be equal to the W XOR X2 XOR X1, okay, or W XOR X1 XOR X2. So our D option is correct. Now let's move to the second question. Okay, I hope this question will be clear to all of you. This is the very basic question of the multiplexer, right? Let's move to the second question. Okay, so in this question, so before starting any question, okay, before starting you try to solve the question, okay, for getting better, okay, confidence in this topic, right? So this is a good question asked in the previous year GATE examination. So here it's given this is the 3 is to 1 3 is to 8 decoder, and this is 8 is to 3 encoder, and these are using this two decoder and the encoder, okay, to get this output, okay, y2 y1 y0, and this is our input, okay. So let's write here our input, okay. So I am writing here x2 x1 and the x, okay. This is our input, okay, and I am writing here output, okay. What will be the output? Y2 y1 y0. This is our output. So first we are going to write all the possible combination 0 0 0 0 1 1, then again 0 0 1 1 0 0, and this is 0 1 0 1 0 0 1. I am going to group this in the group of 2, okay, right? So these are our input, right? So let's see here, okay, let's see here. If our input will be 0 0 0, if our input will be 0 0 and 0, okay, input will be 0 0 and 0, so here op0 will be 1, okay. For 3 is to 8 decoder we have seen that for all the 0 input, this output first 0 output will be selected, that is op0, okay, right? op0 will be selected, so this will be the 1, and rest all will be 0, and rest all will be 0, right? So this, when this op will be equal to 1, so this ip0 will be activated into h20 h23 encoder, so our output will be equal to 0 0 and 0, because this 0 will be activated, right? What is encoder? Is convert any, okay, is convert the any number, okay, into the binary number system, any number system into the binary number system. And what is decoder? It convert any binary number system to the any other number system, right? We have studied all these things in our theory classes, right? So for 0 0 0 we are getting 0 0 0 as the output, right? For 0 0 for 0 0 1, for 0 0 1, okay, for 0 0 1 this output 0 will be 0, this output 0 will be 0, and this output 1 will be 1, okay, and rest all will be 0. So here input 1 will be activated, so the output will be equal to, so the output will be equal to 0 0 and 1, okay, 0 0 and 1. right? Okay, then our last input we have calculated for this. Now we are going for this. Okay, for 0 1 0. Okay, for okay, for 0 0, what will be the our output for 0 1 0? This will be the activated, this will be the activated, and rest will be equal to the 0. Okay, so this op2 will be activated, this op2 will be activated. Okay, this op2 will be activated, rest will be equal to 0. So this op2 is connected to the ip3. Okay, is connected to the ip3. So for 0 1 for 0 1 0, ip3 will be activated, and we are going to get the output like 0 1 1. Okay, 0 1 0 1 1. So for 0 1 0, we are going to get the output 0 1. Right now we have moved to this for 0 1 1. Okay, for input 0 1 1, for 0 1 1, this op3 will be activated. For 0 1 1, this op3 will be activated, this op3 will be activated, or will be equal to 1, and all the other output will be equal to 0. So this op3 is connected to the ip2. So for 0 1 1 as an input, this ip2 will be activated, this ip2 will be activated, this ip2 will be activated, and the output we are going to get corresponding to the ip2 will be 0 1 0, right? Now for 1 0 0, okay, for 1 0 0, how we are going to get? For 1 0 0, for input 1 0 0, this op4 will be activated, this op4 will be activated. Okay, this op4 will be 1, and rest all the output will be equal to the 0, rest all the output will be equal to the 0. Now see where this op4 will be connected, this op4 is connected to the ip6. So for the input 1 0 0, ip6 is activated. For the input 1 0 0, this ip6 will be activated, and now we are going to get this output as now we are going to get this output as 6. This is 1 1 0. Now we are going to get 1 0 for 1 0 0. Okay, now for the input 1 0 1 0 1, for the input 1 0 1, what we are going to get? For the input 1 0 1, okay, for the input 1 0 1, the op5 will be in the output op5 will be equal to the 1, and rest all the output bit will be equal to 0. This op5 will be equal to 1, and rest all the output bit will be equal to 0. So this op5 is connected to ip7. So for the input 1 0 1, for the input 1 0 1, this op5 is connected to the ip7. ip7 will be activated, and the output corresponding to ip7 is 1 1 1, is 1 1 1. So we are going to get the output as 1. Now for this as an input, what is 1 1 0? For the input 1 1 0, which one will be activated? This op6 will be activated, this op6 will be activated. Okay, this op6 will be 1, and all the other output bit will be equal to 0. Now this op6 is connected to the ip4, is connected to the ip4. So for ip4, for active bit at the 4 place, we are going to get the output as 1 0 0, right? 1 0 0 1 0 0. So we are going to get the output 1 0 0 for the input 1 1 0. Now for the input 1 1 1, for the input 1 1 1, for the input 1 1 1, this op7 will be at the op7 output will be at logic high, and all the rest output will be at the logic low. So this op7 is connected to the ip5, this op7 is connected to the ip5. So for this IP5, the logic high will be appear to the IP5. So we are going to get the output as okay 101. Okay, 101. Now we have both the input, as well as the output. Now compare. Okay, for 000 it's we are getting 000. For 001 we are getting 001. Okay, for 010 we are getting 011. For 100 we are getting 110, and for 101 we are getting 111, and for 110 we are getting 100, and for 111 we are getting 101, right? So see on the MSB. Okay, see on the MSB, that is x2 and the that is x2 and the that is x2 and the y2, x2 and the y2. And what we are going to get from here is that x2 will be same as the y2. Okay, so we will write here that y2 will be same as the x2. Now see, okay, now see this y1, for y1 0 0 1. See, y1 will be 1 here, y1 will be 1 here, y1 will be 1 here. Okay, so when y1 will be 1, see here 0 and 1, then again 1. So we cannot say that y1 will be similar to the x1, because in this will be the 1 1 and this will be the 0 0. Now we are going to do, okay, 0 XOR 0, 0 XOR 0, 0. Okay, 0 XOR 0, 0, 0 XOR 1 1, 0 XOR 1 1. Okay, 1 XOR 0, 1, 1 XOR 0, 1, 0 XOR 0, 0, sorry, 1 XOR 1 0, and 1 XOR 1 0. So we can say that this y1 will be equal to x2 XOR x1. Right? Similarly, if we see this y0, we are going to get this. Okay, y0 here we are going to get 1. So 1 XOR 0 will be equal to 1. Now here 1 XOR 0 will be equal to 1. Now here 1 XOR 1 will be equal to 0. Okay, so similarly we will see that y0 will be equal to x1 XOR x0. So this Boolean function, for which type of the code conversion we are going to this we are going to get this Boolean function. So for if we are going to convert, okay, binary, if we are going to convert binary to, okay, binary to gray code, we are going to get this type of the Boolean expression. Okay, this type of the Boolean expression. So we can say that here our output is our correct option is binary to gray converter. It is going to convert binary to binary. This here binary, we are giving here binary, and here we are getting the gray as a output. We are giving the binary input and we are getting the gray output. So this combination, okay, this combination is acting as a binary to gray code converter, right? I suggest you please do this example once again by yourself, and after that we will get some confidence, okay, in this type of the question is asked in the GATE previous year. Okay? Now let's move to the our third question. Okay, so our third question is this. Okay, so this is again is the 4 to 1 marks, and what is asking the logic function implemented by the circuit below. Okay, it's asking the f, what will be the f. Okay, so here it's 0 and here it's 1, and again it's here 0. If we are going to see this is 1 1 and this is 0, so we know the what will be the function, Boolean function of the 4 to 1 marks, that is s1 bar not bar. Okay, I not s1 bar s not 1 plus s1 s2 and plus s1 not. Okay, I3, right? So here S1 we have connected to the P and S0 we have connected to the Q. So we can say P and Q bar and 0, because here I0 0 plus P bar Q and I1 1. Okay, 1 1, right? So we have keep here 1 plus PQ bar, this is 1 plus PQ, again this is 0, PQ again 0, right? So we can see here that P bar Q, P Q bar, this is, it will be equal to the P XOR Q. So our correct option is option D. Okay, our correct option is option P XOR Q. So this is the easy question. Okay, so let's move our third question of the day. This is our third question. Okay, so this is our fourth question. I think this is our fourth question. We have completed 1 2 3. This is our fourth question. Now this is a very good question asked in the previous gate. Okay, so here what it is asking, it is say that we are going to get this 1:8 demultiplexer. Okay, with the data input D in address input. This is a selective line. Okay, S0, S1, S2. Okay, with S0 is the LSB and S2 is the MSB. Okay, right? And Y0 bar to Y7 bar. Okay, as a 8 demultiplex output. Okay, is to be designed using the 2 to 4 decoder. This is the 2 to 4 decoder, and this is also 2 to 4 decoder with enable P bar and the address input not A1, right? In the figure D in S0, S1 and S2 are to be connected. So we have the three input, right? This is the D in, okay, the D in and the S2, S1 and the S0, and it's saying in which order we are going to connect this D in S2 and S0 with the P, Q, R, S. Okay, now this D in S0, S1 and the S0 are to be connected with P, Q, R, S, but not necessarily in this order. The respective input connection to the P, Q, R, S is okay. Now it is saying that we are going to create the 1 to 8 demultiplexer using the 2 to 4 decoder, and there is some logic gate, and it's given our input, okay, data input D in, and this is our selective line. So it's asking the question in which order should we provide this input, okay, D in S2, S1 and the S0. Okay, so we have understood the question properly. Now we are going to solve the question, right? So okay, we know, okay, for the demultiplexer, let me tell here. Okay, 2 to 4 decoder, 2 to 4 decoder. So for 2 to 4 decoder, okay, this is our input A and B, and this is our output, for output, okay, D0, D1, D2 and the D3, right? So A, B, okay, what we are going to get the output here, what we are going to get output here, here we will get the output A bar, B bar, here we will get the output A bar, B, because, and this is the active high decoder, okay, active high, the decoder with the active high, okay, enable, right? So here we will get A, B bar, here we will get A, B, right? It will give the min term, okay, active high decoder will give the min term, we have studied in the theory, right? So if we are going to, if we wish, okay, if we wish this 4 output, okay, this 4 signal as a output, and so we want that only one of the decoder will be acting at a time, okay. So if we want Y0 bar, Y1 bar, Y2 bar and the Y3 bar, and after that Y4 bar, Y5 bar, Y6 bar and the Y7 bar, so we want that only one decoder should be acting at a time, okay, should be acting at a time. right? So how the only one decoder should act at a time if we are going to, okay, provide the enable, okay, this is the active low enable, this is the active low enable, so it will be act for the 0. So if we will provide the logic 0, or say low logic here, if we will provide logic 0 here and we will provide logic 1 here, so this decoder will be work, okay, and this decoder will be work, and this decoder will be not work. Similarly, after some time, if we are provide this 0 to 1, we are going to interchange this 0 to 1 and this 1 to 0, then this decoder will not work and this decoder will be work. So we want that for getting the 1 to 8 demultiplexer, okay, we wish that only one decoder should work at a time, right? So to work one decoder at a time, okay, we are going to give and the active, okay, the low logic at the one of the decoder input, okay. So we are given here 0 and here 1, right? Now if this decoder will be, now concentrate on the this decoder, okay, if this decoder will be work, okay, so if we provide this 0 0 here, if we provide this 0 0 here, so this will be the select, okay, this will be selected. If we provide 0 1 here, then this will be selected. If we provide 1 0 here, then this will be the selected. If we provide 1 1 here, then this one will be selected, right? In the same way, if the enable will be 1 here, so it will be not work. If the enable will be 0 here, then it will be the work. So if we provide, okay, here enable is 0, right? Here enable is 0, here enable is 1, but if the enable will be, okay, will be 0, then this one also activated, like this one also activated. So we are, if for 0 0 this one will be activated, for 0 1 this one will be activated, for 1 0 this one will be activated, and for 1 1 this one will be activated. Now we are going to write this all the four, okay, input, okay. So here we have written 0 0 0 1 1 0 and 1 1, again 0 0 0 1 1 0 and 1 1. This is for the our first decoder and this is our second decoder. So for first decoder to work, okay, we have to provide the enable, okay, as a 0. So here we will provide the enable as a 0, okay, and okay, at the same time this enable should be 1, okay, it should be 1, okay. So at a time when the enable will be 0, this for 0, when the enable will be 0, okay, when the enable bar will be 0, when the enable bar will be 0, we are going to get for 0 0 this one y not bar, and then for 0 1 y1 bar, and for 1 0 this is y2 bar, and the 1 1 y3 bar. And when we are going to make this signal, let me consider this signal as a p, no, not p, p is given here, let me consider this signal as a z. So for z equal to 0, the first decoder is working. For z equal to 1, the second decoder is working, okay. So if z equal to 0, this first decoder will be working, and for 0 0 we are going to get y naught bar, for 0 1 y1 bar, for 1 0 y2 bar, and for 1 1 y3 bar. Similarly, if z will be the 1, okay, z will be the 1, so z will be the present here, this we have considered as z, and z bar will the present here, okay. So for 0 0 we are getting y4 bar, and for 0 1 y5 bar, and for 1 0 y6 bar, and for 1 1 y y7 bar, right? So if we are seeing that this is acting as a selective line, okay. For 0 0 0 we are going to get y naught bar, this one, okay. For 0 0 0 1 we are going to get this, for 0 1 0 we are going to get this, and for 0 1 1 we are going to get this, okay. Now we have seen that this is acting as a selective line, and this is the MSB of the select, and this is the LSB of the selective. So we can say that this is the S2, this is the S, this is the not bar. Okay, we can say that. So this is the clear. Okay, this is acting as MSB, this is acting as LSB, and we can say this is S2 S. Now okay, if we will give the 0 here, okay, if we will give the 0 here, here it will be 0 and here it will be the 1. So whatever this input, this output of the OR gate will be equal to 1. Okay, now if we will give the 1 here, okay, this will be the 1 and this will be the 0, and it depends upon the DIN. So we can say that P is connected to the, so we can say that P is connected to the DIN, okay, and this Q is connected to the S2, okay, and this R and S, this R is connected to the R is N, this R is connected to the S0, and this S is connected to the S1. Okay, please solve this question once again by yourself. Okay, and this is the very good question. Okay, asked in the previous gate here, previous gate. So from this discussion we at least clear that how you are going to connect this D in S2 S1 and the S0. Okay, so P will be connected to the, let me see the option, this P will be connected to the D in, the Q will be connected to the S2, and this R will be connected to the S0, and S will be connected to the S1. So our correct option is D. Right, our correct option will be D. Now let's move our last question of today, this one. I hope this one will be clear to all of you, and if it's not clear, okay, because it is a tricky question and it's really very good question, please solve it by yourself. Okay, and please think that we should work, we have to okay, we have to keep this decoder active at a time, and the same time this decoder should be inactive, right? So for keeping this active and keeping this deactive, we have to provide this enable with logic 0 and this enable with the logic 1, right? So from this point only we have assumed that if we are consider this is as a signal Z, so we at least in our mind we can assume, we can understand that okay, this S2 is MSB. That's why if we are keeping this MSB 0, okay, 0, and we are changing this as 0 0 0 1 1 0 1 1, so this decoder will be work. So we can understand that this, okay, this signal, okay, the output of this signal, or we can say that the P will must be connected to the S2, and this A1 must be connected to the S1, and this A0 must be connected to the what is S0. Okay, similarly please solve this question by yourself once again. Right, now let's move to the our last question of the day. This is our fifth question, right? Question number 5. So in this it's given in the question that okay, for the circuit shown in the figure, okay, the gate for the NOR gate delay, okay, the NOR gate delay is 2 nanosecond. We will write 2 here clearly, 2 nanosecond, and 1.5 nanosecond the max delay is 1.5 nanosecond, and 1 nanosecond is the inverter delay. This is the 1 nanosecond, this is the 1 nano. Now if all PQRS and the T, okay, this is a T, our selective signal, are applied at the same time, okay, and this PQRS and the T are applied at the same time, then the maximum propagation delay in the nanosecond of the circuit will be, so it is okay, it's demanding the maximum propagation delay. Okay, and it's given the delay of the all the circuit. So there will be the two cases, right? Because T is connected to the selective line. So in first case we are going to keep this T as logic 0. In second case we are going to keep this T as a logic 1, right? This T as a logic 1. Here is case second, here is case first. Okay, so in first case we have put that T will be the logic 0. So if T will be the logic 0, so this will be the logic 1 after the 1 nanosecond, right? And for this, when this will be the logic 0, then we are concentrating or we are focusing on the this input rather than this. If this is the logic 0, then 0 I naught will be selected and this I1 will not be selected. Okay, this output Y will be equal to the I naught. Okay, so for T equal to 0, okay, for getting this I naught, okay, let me I1, okay, and again this I naught and this I1, right? So when the T will be equal to 0, for then for getting the I naught, we have to wait for the 2 nanosecond here. So we are going to count this gate delay, and after getting the I naught we have to wait for the 1.5 nanosecond, and when this will be the 0, this will be the 1. Okay, and it's will be 1 after the 1 nanosecond. That will be not count because it's already have been 3.5 nanosecond. So if this selected line will be equal to 1, then this I1 will be selected, and for getting I1 there will be the no delay. Okay, there will be the no delay, and for getting Y there is a delay of the 1.5 nanosecond. So if the T will be equal to 0, then we are going to get the delay of this and get this, this NOR get plus this mux 1. Okay, then this mux 2. Now we are going to calculate the delay. Okay, T of NOR get will be equal to 2 nanosecond plus T of mux 1.5 nanosecond. T of mux 2 will be equal to 1.5 nanosecond. Okay, so total delay will be the 3 and 3 6 nanosecond. Now if T will, we have understood this, right? If T will be the 0, okay, then this will be the 1. Okay, and if T will be the 0, this selective line will be 0, and for 0 we are focusing on the I naught rather than the I1. So for getting I naught we have to wait if Q and R, PQ, RST all applied at the same time. Then for getting the I naught we have to wait for the 2 nanosecond, right? And after getting I naught we have to further wait for the 1.5 nanosecond for this mux. Okay, for getting the output of this mux, and after that the S naught will be 1. So we have to concentrate on I1 rather than I naught. So here this output of the first mux is available. Okay, and here it will not take any delay because there is no delay given for the wire, and it's appear here suddenly when this appear at the output Y node, and we have to work for getting the Y1, for getting the output Y. This is the final output. We have to wait again for the 1.5 nanosecond. So total we are going to wait, okay, for this one for 2 nanosecond and for 1.5 nanosecond, and this again 1.5 nanosecond, right? Now let me clear the figure. Okay, okay, now let me write here. This is again the I naught, this is the I1, and this is again the I naught, this is Y again. Okay, now we are going to take this T will be equal to 1, right? We are going to get this T will be equal to 1. Okay, for this T will be equal to 1, here it will be equal to 0. Okay, right? and the delay of this gate is 2 nanosecond. This is 1.5, this is 1.5, and this is 1. Okay, this is 1, right? So here the t will be available here. Suddenly whenever the t will be the 1 at logic 1, suddenly it appear here at the s0. For t will be the 1, we are going to focus on this I1 rather than I0, because if s0 will be equal to 1, we will get this as an input and we will provide this input to the output. Okay, now when the I1 will be means when we are going to get the I1, okay, after the 1 nanosecond, when PQRST is available at the same time, so after the 1 nanosecond we are going to get this I1. Okay, now for getting the Y0, we are going to wait for the 1.5 nanosecond. We are going to wait for the 1.5 nanosecond, this 1.5 nanosecond, and this is the 1 nanosecond. Now this S0 will be 0, so we are going to concentrate here at Y0, at I0 rather than I1. Okay, so for getting I1 from Y0, we have to wait for again okay, 2 nanosecond, again 2 nanosecond. Okay, so we have to wait for the 2 nanosecond, and for getting this Y, we have to again wait for the 1.9 1.5 nanosecond. So when the t will be equal to 1, so for getting the output y, we have to wait for this t of the AND, this t of the NOT or inverter, we can say here it's the inverter or NOT, both are the same, t of NOT, okay, plus t of 1 plus, okay, plus t of this NOR plus t of this NOR plus t of 2. So here total time is t of NOT 1 nanosecond, t of NOT 1 nanosecond, right? This is the 1 nanosecond plus t of mux 1 1.5 nanosecond plus t of NOR is 2 nanosecond. Okay, t of NOR is 2 nanosecond and t of mux 2 is 1.5 nanosecond. Okay, 5 nanosecond total. We are going to get the delay for the output y is 1.5 1.53. Here it's again coming the 6 nanosecond, right? Here 1.5. okay, here we are going to get here 1 nanosecond, here 1.5 nanosecond, again here 2, okay, and then again here 1.5 nanosecond. So we are going to get here is 3 plus 3 is 6 nanosecond. How these two will be equal? I don't think it will be equal. Let me recheck again. It's asking for the maximum propagation delay, right? So for when the t will be equal to 1, right, for when the t will be the equal to 1, we are concentrating on this. So here the delay of the NOT gate, that is equal to 1 nanosecond, right? Then delay of the mux, that is equal to 1.5 nanosecond. Then here will be the 0. Then we are getting the delay of this, okay, NOR gate, that is equal to the 2 nanosecond, and then delay of this, that is 1.5, right? The total 6 nanosecond. Total 6 nanosecond, right? When the logic will be 0, let's say when the t will be 0, then when this t will be the 0, okay, then for we are concentrating on this. On for getting this, we have to wait for 2 nanosecond, okay, 2 nanosecond, and then we have to wait for this 1.5 nanosecond, and this 1.5, it will be the equal to the 5 nanosecond, right? 1.5 and 1.5 plus 2, this will be equal to the 5 nanosecond. So this is the 5 nanosecond. So maximum propagation delay is okay. So maximum propagation delay is 6 nanosecond. Where we were the last question, right? So here, okay, here when the t will be the logic 0, is taking total 5 nanosecond for getting the output y, and when the t will be the logic 1, it is getting 6 nanosecond for getting the output y. So the maximum delay is the 6 nanosecond. So we have covered the 5 question in this, okay, in this lecture, okay, or in this video we have covered the 5 question, okay, where this 2 question is really very important. First one, this question is really very important, and again where we are going to, and this question is also really very important, because we are going to get we are going to do the maximum error in this type of tricky question. Rest all good, okay, rest all are good. This one is also little bit tricky question. When we are going to miss any of this, we are end up with the wrong question, right? Sorry, wrong answer. Okay, so in this video we have completed the 5 question. Okay, please okay, please do this question again, once again, by yourself, right? And in the next video we will going to solve some more question, or we are going to start the half adder, half substructure, full adder, full substructure, comparator, and then all the carry adder. Okay, right? Okay, thank you for attending the classes. Thank you.